Picture this. A massive, multi-million-dollar rocket is blasting vertically into the sky, just absolutely tearing through the atmosphere. Now put yourself in the shoes of the engineer in charge of the robotic camera on the ground tracking this thing. How do you actually program that camera to tilt upward at the exact, precise speed to keep that rapidly accelerating rocket perfectly centered in your frame? Think about it. If it tilts too slowly, the rocket vanishes out the top. Too fast, you're just filming empty sky. This is a high-stakes problem, right? And the solution, well, it isn't guesswork. It's calculus.
Welcome to The Explainer. Today we're mastering related rates. And look, we aren't just going to stare at dry textbook equations today. Oh no, we're unlocking a really practical tool for measuring our incredibly dynamic, moving world. Here's our quick roadmap for The Explainer. We'll start off with connecting rates of change. Then I'll hand you a foolproof 5-step strategy. Once you've got that toolkit, we'll tackle 3 real-world trials: tracking an airplane overhead, the tricky leaking funnel problem, and finally tracking that rocket launch.
All right. Section 1. Connecting rates of change. When quantities move together. You see, in the real world, things rarely change in total isolation. When one thing moves or shifts or grows, it almost always forces something else to do the exact same thing right along with it. So what are related rates exactly? Well, it's simply calculating one rate of change by figuring out its mathematical relationship to another rate of change that you already know. Calculus is basically our secret key here. It lets us peek under the hood of reality to find those hidden mathematical gears connecting all these moving parts. Take a look at this spherical balloon expanding over 3 stages. It illustrates the concept perfectly. As you pump air into it at a steady rate, the volume of the balloon goes up, right? But at the exact same time, the radius of the balloon is pushing outward. Now, volume and radius are 2 completely distinct physical measurements, but because they belong to the same physical object, their rates of change over time are permanently linked together. If you know how fast the air is going in, calculus lets you figure out exactly how fast that rubber is expanding outward. It's pretty cool.
Moving on to Section 2, the 5-step strategy, your ultimate problem-solving toolkit.
We've all been there. You're faced with this massive, terrifying paragraph of text about speeding planes or leaking tanks, and it's so easy to just freeze up. But if you relentlessly apply this 5-step approach, you've essentially got a hero's toolkit to conquer literally any related rates problem. Let's walk through it. Step 1, assign symbols to variables and draw a picture. Seriously, get it out of your head and onto paper. Step 2, state your knowns and unknowns using those variables. Step 3, find a geometric or algebraic equation that relates them all together. Step 4, differentiate both sides with respect to time using the chain rule. And finally, Step 5, substitute all your known values in and solve for the one you want. Trust me, following this exact sequence is the absolute best way to cut through the noise. But wait, before we go any further, I need to issue a massive warning. The absolute crucial rule is this: do not substitute known values too soon. I'm telling you, this is the ultimate trap. If you plug a specific number into your equation before doing the calculus in Step 4, that moving, changing variable falsely becomes a constant. And what happens when you take the derivative of a constant? Boom, it becomes 0. You literally destroy the math. Always wait until Step 5 to plug in your specific snapshot and time numbers.
Okay, Section 3, tracking an airplane overhead. Trial 1, the setup.
Let's put our toolkit to work. Step 1, we draw the scene. We've got an observer standing on the ground near a radio tower. A plane is flying horizontally away from them, cruising at a constant elevation of 4,000 feet. We can easily sketch out a right triangle here. The horizontal distance from our observer to the spot directly under the plane, let's call that x. And the direct, diagonal line of sight from the observer to the actual plane, we'll call that s.
Now for Step 2, translating this physical scene into our knowns and unknowns. The plane is flying at a speed of 600 feet per second. In our math model, that physical speed is just the rate at which our horizontal distance, x, is changing over time, so dx dt equals 600. The height? That's a rock-solid constant, 4,000 feet. So what are we trying to find? We want to figure out how fast that diagonal line of sight distance is increasing, which is ds dt, at the exact split-second moment when the plane is exactly 3,000 feet away horizontally.
For Step 3, we need an equation. Since we've got a right triangle, we just pull the trusty Pythagorean theorem out of our geometric toolbox. X squared plus 4,000 squared equals s squared. Notice how we plugged in that 4,000 right off the bat? That's because the altitude never changes. It's a true constant. But x and s, we leave those as variables because they are actively changing over time. Next, step 4, we differentiate with respect to time to get our related rates. And finally, step 5, we substitute our specific moment in time where x is 3000, find our corresponding s value of 5000, and just solve it out. The math reveals that the distance between the observer and the plane is increasing at exactly 360 feet per second. Boom, trial 1 in the bag.
Moving right along. Section 4, the leaking funnel problem. Trial 2, the complication.
We are definitely kicking the difficulty up a notch here. Check out this funnel, shaped like an inverted cone. The whole thing is 2 feet high, and it's got a radius of 1 foot up at the very top. Now, water is draining out the bottom at a constant rate of 0.03 cubic feet per second. As that water drains, think about what's happening. Both its height and its surface radius are shrinking simultaneously.
Let's map it out. We know the volume is changing, so dV dt is negative 0.03. It's negative because, of course, the water is draining out. And what we need to find is how fast the water level itself is dropping. That's dH dt. At the exact moment when the water's height, h, is exactly half a foot.
But here is the catch. The classic formula for the volume of a cone uses both radius r and height h. If we try to take the derivative right now, we'll end up with a tangled, unsolvable mess of variables, mostly because we don't know anything about the rate the radius is changing. So we need a clever little trick to get rid of r. Look at the cross-section of that cone. The water actually forms a small triangle inside the larger triangle of the funnel itself. Because they share the exact same angles, they are what we call similar triangles. That means their proportions are identical. The big funnel's radius-to-height ratio is 1:2, so the water's radius-to-height ratio has to be 1:2 as well, which means r will always equal h divided by 2. We can take that and substitute it right into our volume formula, totally eliminating the r variable before we even touch the calculus. From there, we just differentiate and solve like normal, finding that the water height is dropping at roughly negative 0.153 feet per second.
Now for the grand finale, Section 5, Tracking the Rocket Launch. Trial 3, the boss fight. We are going to use everything we've learned today to answer the exact question we started this explainer with. Let's set the stage using step 1 and draw it out. A robotic tracking camera is bolted to the ground 5,000 feet away from the launch pad. The rocket takes off straight up. The snapshot in time that we actually care about is when the rocket is exactly 1,000 feet up in the air, at which point its upward velocity is 600 feet per second.
Let's lay out our final knowns and unknowns. The rate the height is changing, dH dt, is 600. The horizontal distance over to the pad is our constant, 5,000. But what's the unknown? What's the actual goal here? Notice we aren't looking for a distance this time. The camera has to physically tilt, so we're looking for an angle. We need to calculate the exact rate of change for the camera's angle of elevation, which we'll call d theta dt, so its motorized mount can be programmed perfectly, ensuring we never lose sight of that speeding rocket.
I honestly love this side-by-side view. It so beautifully bridges the gap between raw, messy reality and clean mathematical abstraction. On the left side, you have the violent, chaotic, smoky reality of a massive rocket launch. On the right, the crisp, simple right triangle that models it. That physical camera, it just corresponds to the bottom left vertex of our triangle. The physical rocket is the top right point, and the actual altitude is just the vertical leg h. By distilling the chaotic real world into this simple geometry, we literally gain the power to predict it.
So, for step 3, what's our equation? We need something that connects a height, a constant adjacent distance, and an angle. That absolutely calls for trigonometry, specifically the tangent function. The tangent of our angle theta equals the opposite side, our height h, divided by the adjacent side, which is our constant 5,000. So tangent theta equals h over 5,000. Then we hit step 4, taking the derivative with respect to time using our chain rule. Now, the derivative of tangent is secant squared, giving us secant squared theta times d theta over dt equals 1 over 5,000 times dh over dt. We find the hypotenuse at our specific snapshot moment to evaluate secant, plug in our upward velocity of 600, and finally isolate our target rate.
And there it is. The math produces this incredibly elegant, exact fraction, 3 over 26. The camera must tilt its lens upward at a rate of precisely 3/26 radians per second. If the tracking software inputs that exact rotational speed at that exact millisecond, the rocket stays flawlessly centered in the crosshairs. You've officially defeated the boss fight. You've just used related rates to engineer a real-world, high-stakes solution. As we wrap up this explainer, I want to leave you with a bit of a provocative challenge pulled straight from the source material. Imagine you're looking at an air traffic control radar. Two airplanes are flying at the exact same altitude toward the exact same airport. Airplane A is flying east at 250 miles per hour, and airplane B is flying north at 300 miles per hour. When they are 30 miles and 40 miles away respectively, how fast is the distance between them closing? Are they on a collision course? Grab a piece of paper, draw out the picture, and use your new 5-step related rates toolkit to find out. Thanks so much for learning with me today, and I'll see you in the next one.